Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample of data to say something about a larger population. A common application of statistical inference is using information from a sample to test a claim you might have about a population mean or proportion. Here's an example of a claim that I have about a population mean, and that is I think that students study more than an average of 5 hours per day. That's a claim I'm making about all students, or the population of all students. The first step is to write out the hypotheses, and the alternative hypothesis is a statement of your claim. So the alternative hypothesis, which is indicated by H subscript A, is mu. Mu stands for population mean, is greater than 5, versus a null hypothesis that mu is less than or equal to 5. The second step is setting your significance level, which is written out as an alpha. So alpha in this case is 5%. I just happen to set that as the researcher. I could have done this hypothesis test with an alpha of 1% or 10%, but I happen to choose 5%. This means that there's a 5% chance that I might mistakenly reject the null in favor of my claim. The third step of doing a hypothesis test is actually the fun part of doing the research. So I went out and I collected data on a random sample of 30 students and got a sample mean value of 7 hours of studying per day with a standard deviation of 4. Using this information that I collected, I can calculate the test statistic. Since this is a hypothesis test about a population mean value, it's a t-statistic. So my t-statistic is 2.74. That's 7, which is the value from my research. That's the sample mean value I calculated. I subtracted from that 5, which is the value from the null hypothesis. And I divided this difference of 2 by the standard error of the sampling distribution for a sample mean value, which is S divided by the square root of n, where S stands for the sample standard deviation, which was 4, divided by the square root of 30, which was my sample size. I can interpret this test statistic of t equals 2.74 to mean that the value for my research, or the sample mean value, is 2.74 standard errors away from the value from the null hypothesis. And the farther that you're away from the null hypothesis, the greater the chance that you'll be able to reject the null in favor of the alternative, which is your claim. The fourth step of conducting a hypothesis test is finding what we call the p-value. And the p-value is actually the strength of the evidence in favor of the null hypothesis. So if you have a high p-value, that means there's strong evidence for the null hypothesis, which means you're unlikely to reject it. Whereas if you have a low value for a p-value, that means there's weak evidence for the null hypothesis and you're more likely to reject it. The p-value is interpreted as the probability that if the null hypothesis is true, you could get a value that is greater than or equal to the test statistic that you actually calculated from your sample. If you get a large percentage for the p-value, that means that there's a pretty high percentage that you could have actually gotten the value that you got for your test statistic if the null were true. In other words, there's strong evidence for the null. If you get a low percentage for the p-value, that means that there's a pretty small probability that if the null hypothesis were true, you could have gotten a value that was more extreme than the test statistic that you got from your sample. To find the p-value, and again, this is the hypothesis test about a population mean value, we're going to use the t-distribution. And you see that I put in the value for 2.74. That's the test statistic that we found. And since the claim in the alternative hypothesis was a greater than claim, we're actually interested in the right-hand side tail of the t-distribution. So what we're looking for here is the area in the right tail of the t-distribution that is equal to or greater than 2.74, of the test statistic that we found. So now we'll go to the t-distribution table. You might recall that the t-distribution table shows the upper tail for a given degrees of freedom. Since we had a sample size of 30, we're using 29 degrees of freedom, so that's n minus 1. So 30 minus 1 is 29. And we're looking for the value of 2.74. If you go across the row for 29 degrees of freedom, unfortunately we can't find the value of 2.74. We find 2.462 and 2.756. So 2.74 is somewhere between those two values, which means that between 0.5%, or 0.005, and 1%, which is 0.01, is the area in the upper tail that's greater than 2.74 for a t-statistic. So this is what it looks like on the t-distribution. You see the t-statistic of 2.74, and with 29 degrees of freedom, between 0.5% and 1% of the distribution is greater than a t-statistic of 2.74. So we interpret the p-value to mean that there's between a 0.5% and 1% chance that if the null hypothesis were true, in other words, if the average amount of time spent studying was less than or equal to 5 hours, that I could have gotten a value that is greater than or equal to the test statistic that we got from our researcher from the sample. In other words, there's very weak evidence in favor of the null hypothesis. So sure, there's a chance that I could have gotten the value I got from my research if the null hypothesis were true, but that chance is between 0.5% and 1%. So it's very unlikely that the null is true. So chances are that my claim is actually true, and that we'll be able to find support for my claim.